total momentum equal to the total momentum before a collision is equal to the total momentum after a collision. That's where we were at last day. What? And we said that that would expand out to being MA VA plus MB VB equals MA VA primed plus MB VB primed. And I'm going to call that equation 1. Now, we defined out like a handful of equations last day. We actually defined out like 5 equations, a system of 5 equations, and they were special case equations. Some of them were ones where energy was lost, but the objects didn't stick together. Some where no energy was lost and they didn't stick together, and some where energy was lost and they did stick together. And we outlined what elastic, inelastic, and perfectly elastic collisions were. Right now, I just want to focus on a perfectly elastic, the one that I said was the rarest form of collision, where EK is equal to EK primed, or I could say EK total is equal to EK total primed, but it would expand out to being 1/2 M A VA squared plus 1/2 MB VB squared, where the A's and B's are talking about 2 different bodies, and when we're priming things, we're talking about the after. So VA prime would be the final speed. And of course we recognize that we're not priming the masses because the masses of these 2 bodies that have collided or whatever is staying the same, but the speeds of these 2 masses is going to change. So we've got an equation 1 and an equation 2. One thing that you notice, and you'll see this, well, we'll see it today, but you also see it if you do one-dimensional collisions with conservation of energy. And if you have started the homework, maybe you've encountered it already. But you notice that the first equation is a linear equation in terms of the V's, whereas the other one, in terms of the V's at least, is not. So if I'm going to use a system of equations, if I'm solving for a V, there's going to be some squaring going on, and that's going to be complicated because this is a 4-term expression. Well, both of them are 4-term expressions. So you can kind of imagine, if you're able to imagine in math, if I was isolating for VB prime, for example, and I subbed in the new expression for VB primed, isolated for VB primed, into the VB primed spot in equation 2, this is a 3-term expression that now has to be squared. That's not trivial. That's annoying, right? That's something that's more than just a binomial times a binomial. That's a trinomial squared. And that's not something that makes a lot of us happy, but it's just going to be a thing. Ugh. Okay, so not conceptually hard to wrap your head around, but like mechanically a pain in the bum. All right, so I've got mass A and I recorded that. Bum, you heard it. Harsh language, it really is. So I've got mass A and mass B. These are 2 pieces of cheese. I'm choosing cheddar and gorgonzola because I feel like if I shot them at each other, there wouldn't be any damage, okay? So I have mass A, 2.00 kilograms, and the way cheese prices are going these days, that's a valuable piece of cheese right there. Mass B, gorgonzola, even price here, 2.50 kilograms. And they're going to get shot at each other from dairy cannons, obviously, at 2.30 meters per second towards the right, and at 0.500 meters per second. Slow launch speed for the gorgonzola. Don't want to damage the precious gorgonzola. 0.500 meters per second, okay? We'll give ourselves a reference frame. Right, left, positive, negative. Now, I've got a conservation of energy thing going on up here. This is what the equation would be if there was perfect conservation of energy. According to this expression, or this description, if the cheeses stick together when they collide, what kind of collision is this? There's 3 options, just to remind you. We got perfectly elastic, we've got, some people are going to call it partially elastic. Some people will just say imperfectly elastic. Other people will just say elastic. All those ones there are ones where energy is lost, and they do not stick together, okay? They all mean the same thing, essentially, okay? Perfectly elastic is when all the energy is conserved and they don't stick together. So we just claimed that it's going to stick together, so it's neither of those two options, neither option 1 nor option 2. Option 3 is that perfectly inelastic. And perfectly inelastic means that these two objects, when they collide, are going to stick together, and there is energy loss. So the equation 2 that we just chose up here, or wrote up here, is not necessarily a helpful equation for us right now, because this kind of indicates that they're traveling off separately as independent bodies, right? So we may have to try something different with this. Notice part B has us come at it with energy, but for part A, since momentum is always conserved, maybe we could make use of equation 1. Okay, so that's what I want to sort of explore here. If the cheeses stick together when they collide, find their final velocity. So if I start off with that equation 1 at the top of the page, I could say MAVA plus MBVB equals MAVB primed plus the A primed, that index, MBVB primed. And we could just say let VA primed equal VB primed equal V primed. And the reason that we would do that is if they stick together, the VA primed and the VB primed are going to be the same value, right? Okay, so we kind of developed that yesterday, but I just want to make sure that we can see where it's developing from in the context of cheeses. And then you're like, oh, I can just factor the V primed off. Oops. And then I can divide both sides by the binomial. So I get V primed is equal to and there's always this deep desire to try and cancel things, but we can't. There's no canceling that can be done there, right? Now, I've kind of painted myself into another corner here, so I'm just going to do a bad thing and make that be equal to, I'll sub in my values. Now we called to the right positive, so that 2.30 is positive, but I'm drawing attention to the positive negative of the reference frame right now because we've got to make sure that the VB comes in as a negative. Even if it's a small VB. So somebody with a calculator, help me out. I think the answer starts with a 7, but I have these trust issues with myself. And it's small. It's not a big value. Yeah?
0.74 repeated.
Nice. 0.74 repeated meters per second. And positive or negative?
Positive.
Positive. I'm positive. All right, so we'll give ourselves a little partition here. So we can say V primed is approximately equal to, what, we had 3 sig figs here? 0.744 meters per second, and positive was to the right. And we could have ourselves a little therefore statement, just to put it in context. The final velocity of this system, the cheesy system, is 0.744 meters per second to the right. All right, Part B says find the amount of energy that's lost by the cheesy system. Okay, so we could start off EKA plus EKB equals EKA primed plus EKB primed. But it's suggesting that energy is lost, and we actually hashed out that when systems stick together like this, energy is always going to be lost. So the way that we deal with this is we're just going to tack on an energy lost term onto that. And the way that we dealt with it further last day was to say 1/2 MAVA squared plus 1/2 MBVB squared equals 1/2. Actually, can I just make a quick simplification here? That term, EKA primed plus EKB primed, if the two masses are going to stick together, doesn't it make sense that I could actually write it as 1/2 mass A plus mass B? Because they're now stuck together, right? And they're stuck together traveling at the same speed, so that V primed from the previous statement squared. Does that make sense to people? This is all big one big mega cheese mass. Mass A, mass B combo mass. Big cheese combo. Sounds like something at a fast food place. So mass A plus mass B, lactose intolerant nightmare. All right. Plus E lost. And actually, as I look at this, we know all the values except E lost. So it's kind of ugly, but E lost is, and we can just take all that stuff except for E lost over to the other side as a negative. So I'm just going to write it as the expression, then we can finally sub in the values, and hopefully we have enough space to fit all this onto one page. Notice I can't combine the two masses before because they weren't stuck together before, right? They were on a collision course. I'm going to start all the way over on the left-hand side because I have this fear that once I sub in these values, it's going to sort of swamp the page. We're going to use the unrounded version of V primed just to make sure we all are on the same page with that one. Make sure you get as many 4s in there as you can, unless you've held it in memory. What do you get?
Oh no, I have a question.
Oh sure, yeah.
Since VB is going like to the left and it's negative, wouldn't it be negative in the equation or no?
Oh yeah, good point. I mean, we could put that 0.5 in as a negative, but if you're going to square it, it doesn't matter.
Oh, okay.
Nice thing about energy is it doesn't care. Momentum does care. Momentum's a vector. That's good. Somebody else might not have asked. I like that question. All right, does anybody get an energy loss? I think it starts with a 4. What do you get? 357,044. All right. And that's joules. And we were floating at 3 sig figs, so about 4.36 joules. Beautiful. All right, that sounds good. Actually, that's exactly what my notes told me too, but I never trust me. All right, and to make sure that we got this, we've got these two system equations, and I want to pop back one more time to the previous page. You got it in your notes, but I want to make sure that we've got this. We actually have a system not just of two equations, we really hashed it out as 5 equations. So we've got conservation of momentum when the objects stick together, mass 1 plus mass 2 times the v prime of the system. We've got perfectly elastic energy collisions where the objects don't stick together and energy is also conserved. We have perfectly inelastic or partially elastic energy conservation where they don't stick together and energy is lost. But that could also be expressed like we just did, where the energy is lost, but we do the kinetic energies as a combo mass, like the cheesy combo we just looked at, right? And then finally, in all circumstances, the momentum is going to be conserved before and after. And what you need to do when you solve these problems is you're choosing which conservation of energy and which conservation of momentum expression you're going to have for your system of equations. That's it. Sounds good? Right.
Could you go up to where you like or assign them?
Yeah, I can go back to the previous page. I just wanted to make sure.
To like up in the page where you
Oh, yeah.
wrote the letter.
Sure, yeah. So these are the A, B, C, D, E. And then in terms of which collision types they get assigned to, those are the collision types they get assigned to in a quick little description, okay?